Thanks for joining. We're about to do some practice problems, which is one of the best ways that we have to help us learn. Now, if you haven't tried these problems yourself, please try them yourself first. There's this beautiful button. It's somewhere along here called pause. Make use of it. See the problem? Pause. Try it yourself. Then if you need to, you can unpause and we can compare answers. In this way, you get engaged, you'll learn, you'll succeed. And that's what we want, your success. Let's get going. The position of a spaceship at time t is given by r of t is 2 plus 3t minus sine 2t, x part, 5e to the t minus 2e to the 2t, that's the y part, 4 cosine t plus t squared, that's the z part. The spaceship stops its engines and coasts along the line tangent to its path at time t equals 0. Find integers a, b, and c so that a, b, c represents the spaceship's position at t equals 3. Okay, so what's going on? Well, the idea, let's talk about the idea, is that there's a spaceship, and a spaceship has rockets, and it's able to control its path to some degree. And so it doesn't go in a straight line, it moves around. And so maybe it's doing that. But unbeknownst to its plan, it says, hey, actually, you're going to stop here at time t equals 0, and then instead of going along your planned path, you're going to go off this way. In other words, you're going to keep going in the direction of motion that you're currently going. And then you're going to do that for 3 seconds. I'm assuming this is 3 seconds, but it could be minutes, days, whatever. 3 pieces of time. And the question is, where do you end up? That's our goal. Okay. Well, how do we go about doing all of this? Well, that's not so hard to imagine because we know we're going to go along the tangent line. What's the clue that we're doing the tangent line? Well, it says line tangent. Okay? It's like telling you, hey, line tangent. So, idea. We need to find the tangent line at time 0. All right, so here we go. I'm going to write down r of t again for reference, just because I want it right next to me when I take derivatives. 2 plus 3t minus sine of 2t, 5e to the t minus 2e to the 2t, and 4 cosine of t plus t squared. Okay, now term by term, take a derivative. And the secret to multivariable calculus is it's like single variable calculus. You just do it multiple times. All right, so derivative of 2 is 0, derivative of 3t is 3, derivative of sine is cosine, and it'll be cosine 2t, and then by the chain rule, 2 comes out. So minus 2 cosine 2t, comma. Derivative of e to the t, great. Derivative of e to the 2t will be e to the 2t, and then chain rule, 2 comes down. So now it'll be minus 4e to the 2t, comma, and derivative of cosine, negative sine, so minus 4 sine t, and then derivative of t is 1, and derivative of t squared is 2t. Okay. Now, when we're looking for a tangent line, we don't want functions, we want numbers. So we need to evaluate at time 0. So here we go. R of 0 is 2 plus 0 minus 0, right? Sine of 0 is 0. So 2. E to the 0 is 1. So we get 5 minus 2, 3. Cosine of 0 is 1, then 0 and 0, 4. All right, so there's our r of 0. And at the same time, we'll do r prime of 0. We can do it right below it.
r prime is 0. 3 minus 2, because cosine of 0 is 1. 3 minus 2, 1. E to the 0 is still 1, so we get 5 minus 4, 1. And sine of 0 is 0, so you get 0 plus 1 plus 0, 1. 1, 1, 1. All right, we really won on this problem. Okay, all right. Now, we're going to put these together. And we say, okay, so here we go. Our tangent line, or the line tangent, we're going to make a tangent line, we'll get the following. All right, making notes to self. Note to self, make tangent line. X equals, Y equals, Z equals. We get 2, 3, 4 is the point. So 2, 3, 4, there's our point. And then plus 1 times t plus 1 times t plus 1 times t. Right? So as a reminder, what do we have? This is our point. And there's our direction vector. So those are the pieces that make up our line. So that tells us where we're at any given time. So what's the last thing for us to do? Well, we go for 3 seconds. Or again, I said seconds. Nowhere in here does it actually say the length of the time, but time t equals 3. And so plug in t equals 3. So when we plug in t equals 3, what do we get? Well, we get 2 plus 3, which is 5, 3 plus 3, which is 6, and 4 plus 3, which is 7. 5, 6, 7. And there we go. So really, I guess technically we would say A is 5, B is 6, and C is 7. All right, done, right? We are. But I want to pause and wax a little bit philosophical here, because there's a subtlety that I think we might gloss over, and some people feel very uncomfortable, and some people don't even think there's a subtlety here. Which is to say that when we use this t, we're kind of using it in 2 different ways. So let me explain what I mean by that. So what we have is really have 2 curves. One of them is the curve that this r of t is, the rocket is. Then there's the second curve, which is this tangent line. And so they're separate curves. And so they actually have independent time variables. And so what this t represents is tied to r of t. What this t represents is tied to this line, this tangent line. We should technically use a different symbol, but math was kind of running short of symbols, so they did a little bit of recycling. And so one of the things you might say is, wait, aren't we somehow supposed to be plugging 3 back into this r? And you'll quickly discover you're going to get terrible numbers. And that's one of the reasons why they wanted to emphasize the word integers. You're not going to get great numbers plugging in 3 and getting like e cubed and e to the 6. Hopeless. Those aren't integers. And so it's just trying to emphasize, it's like, no, it's not plugging in 3 into this curve. It's plugging 3 into that curve. And so there can be some ambiguity. And so be careful. Think about, okay, it's the time, but time on which curve? And especially when you have 2 curves interacting, you may say, oh, well, okay, do they ever cross? Their curves could cross, but at different times. So it's different from the curves sort of colliding, where you'd have the same point at the same time. So anyways, that's just my word of philosophizing. I think I called it a minute ago. Be careful. Think about what t represents when you're solving these problems, and how different curves have different times, and you may need to think about them in slightly different ways. Okay, but anyways, that's this problem. On to the next one. The parametric curves R of t is 2 cosine t, 3 sine t minus 2 cosine t, sine 4t minus cosine t, and S of t, 2 sine 7 halves t, sine 2t plus 2 sine half t, and cosine 2t plus 4 sine t. Lots of trig going on here. Intersect when t equals pi. So this is, you have the two curves, they're doing whatever they want, but all of a sudden at boom, at pi, they're in the same location at the same time. So if you plug it in, for instance, 2 times cosine of pi is negative 2. Sine of 7 pi halves, well, that's somewhere, right? And, well, it turns out that's the angle pointing straight down. So that's sine of that is negative 1. So you have negative 2 in that slot. And you go through slot by slot, and lo and behold, they're at the same point. All right, now what is it we're looking for, though? We're not necessarily looking for the point. What are we asked? Determine cosine theta, where theta is the angle formed by their tangent vectors at the point of intersection. All right, now there's a couple of clues here, and that first clue is cosine theta. Now, when we see cosine theta, we're like, we know something that involves cosine theta, and that is dot product. So recall that u dot v, I'll make these little vectors just to emphasize, is magnitude of u, magnitude of v, cosine theta. And another way to say this is to say, okay, so if I want cosine theta, I take the dot product and I divide by the magnitudes of these vectors. All right, so now we know how to find cosine theta. So that it specifies cosine theta is really helping us know where to go. So we're going to have to find some vectors and carry this out. Now, which vectors? Well, the problem helps tell us that too. See, problems want us to succeed. And it says, well, the tangent vectors. Now you might say, how does one find this? And we say, okay, so the vectors, the tangent vectors, those are the direction vectors, pointing in the direction of motion. In other words, if we were to think of these curves as zooming in, they would look like little lines crossing. And then what the tangent vectors are talking about is, what is the direction vector of those tangent lines? So where do we find these vectors? Well, the answer is that these vectors are going to be r prime and s prime at the point of at the point of intersection, and so that happens at time pi. So these are going to be our u and v. So now we kind of have a plan. We're going to compute r prime. We're going to compute s prime. We're going to plug in pi into these two vectors, these two functions, get two vectors out, and then carry out the computation. Okay, well, we have a plan, but we still have to do it. So let's do it. Let's start with r prime. Okay, so we're going to be very patient here because there's a lot of terms. And the good news is it's all sines and cosines. So quick recap, derivative of sine is positive cosine, derivative of cosine, negative sine, and don't forget the chain rule. So with all that in place, here we go. Derivative of cosine was negative sine, so minus 2 sine t. All right, that's that entry. Derivative of sine is positive cosine. Derivative of cosine is negative sine, minus, so that'll become a plus 2 sine t. All right, derivative of sine is cosine. Don't forget the chain rule. So that's 4 cosine 4t. And the derivative of cosine, negative sine, so that'll be plus sine of t. And you might say, well, if we make a small mistake but it doesn't matter, will we still lose points? Yeah, it's possible. So pay attention. Pay attention. We want to get all the points. So we're going to make sure we're going to be careful here. All right, derivative of sine is going to be a cosine. Now, let's Be careful. Because we also pull out the 7/2. We have a 2 in front. 2 times 7/2 will give us a 7. So it's 7 cosine of 7/2 t. Derivative of sine is again cosine. Don't forget to bring out the 2 by the chain rule. So 2 cosine 2t. Derivative of sine is cosine. And so that'll be a cosine. But we have this half, so 2 times half makes 1. So plus cosine 1/2 t. All right, derivative of cosine, negative sine, don't forget the 2, minus 2 sine 2t. And the derivative of sine is cosine, 4 cosine t. Okay, now we're doing great. We have our plan in place, right? We're taking the derivatives because we need our direction vectors, which come from plugging in our point where they intersect. We know the time. So we say, okay, now r prime of pi and s prime of pi. So let's go through and figure these things out. Okay, so sine of pi is 0. So that makes that term 0. We maybe can write down some values. Sine of pi is 0. If you think in terms of the unit circle here, pi is right over here. And cosine of pi is -1. Okay, so cosine of pi is -1. Sine of pi is 0, so that's -3 plus 2. So that's -3. And 4 pi. So 4 pi will go around the circle and be back where you started. So cosine of 4 pi is 1 because you're back over here. Okay, and then sine of pi, well, it's still 0. Okay, so 0 minus 3, and then we're going to be at 4. Okay, s prime of pi. What do we have? Okay, cosine 7 pi halves. So we have to think about where is 7 pi halves. And that can be a little bit tricky, but what is 7 pi halves? Okay. Well, if we think about 7 pi halves, what can we say? It's almost 8 pi halves, right? You're right? So that's like cosine of 4 pi minus pi halves. Now you're probably thinking, oh, why think of it that way? Well, we know how to do 4 pi. That's 2 full ways around and then back pi halves. So we're down here. So what is cosine of 7 pi halves? It's 0. Wow. Okay. Well, that might make the computations pretty easy. Okay, good. Comma. Okay, cosine of 2 pi. Well, we haven't done that yet, but that's just a full circle around. So cosine of 2 pi is equal to 1. Cosine of pi halves, by the way, is 0, because that's up here. That's just 90 degrees. So what do we have? We have 2 times 1 plus 0, so that's a 2. And then we have sine of 2 pi. Well, sine of 2 pi is 0. It's like sine of 0. So we have 0 here, and we have cosine of pi, and cosine of pi is -1. So -4. All right, there we go. Those are our values. Now, what do we do? What do we do? Well, we just need to go through and carry out our computation, and we're basically in our home stretch. So, cosine of theta is, we're going to take the dot product of these two vectors, dot 0, 2, -4, over the magnitude of these two vectors. Okay, so we have to remember how to do the dot product, and we have to remember how to do magnitude. So for the dot product, we're multiplying corresponding entries. So 0 times 0 is 0. -3 times 2, -6. 4 times -4, -16. Now magnitude involves a square root, and you square the entries. So 0 squared is 0, negative 3 squared is 9, 4 squared is 16, and then another square root, 0 squared, 2 squared is 4, and negative 4 squared is 16. Don't know why I put 0 squared, but all right. So upstairs, negative 22. Downstairs, we have a square root of 25 and a square root of 20. Now you can do a little bit to clean this up. For instance, square root of 25, this is the same as 5. Square root of 20, that's 4 times 5, which makes this 2 times square root of 5. And, there's a 2 that goes both into upstairs and downstairs. So if we did cancel the 2, that's minus 11 over 2 square root of 5. And there we go. Ta-da! Whoops. Copy mistake. I wasn't paying attention. All right, see the 2 goes in. So it's not the 2 that's left, it's the 5 that's left. I was thinking like, wait a second, that can't be right. 2 root 5, that's small 11. You can't end up with a number that is somehow bigger in size than 1. And so yeah, okay. So there we go. Okay, good. Oh, phew. Crisis averted. Crisis averted. And all right, that's the idea. Woohoo! Let's keep going. The set of points equidistant from points 3, 5, 4. So this is just the name of the point, 3, 5, 4. It's called point P. And minus 1, minus 1, minus 6, we call that point Q, is a plane. And it has an equation. AX plus BY plus CZ equals 3. Find A, B, and C. Okay, now there's actually 2 ways to do it. One way is to say, let's take advantage of the word equidistant. You might say, okay, well, great. What does equidistant mean? Well, what does it mean? It means that they have the same distance. And, okay, so how can one do that? Well, we just say, let's compute the distance to P. And that would be the square root of x minus 3 squared plus y minus 5 squared plus z minus 4 squared. Okay, so that's distance to P. And then we say, okay, now compute the distance to Q. You might say, okay, well, we can do that. That's the square root of, and I'm just thinking of x, y, z as a point in the plane. We have our x minus 1, so that's x plus 1 squared, plus y plus 1 squared, plus z plus 6 squared. Okay, so here is our distance to Q. And what do we know about these 2 distances? Well, they're equa. What does equa mean? Equidistant means they're the same. So, put another way, hey, these are equal. Now, you say solve. And what does that mean? Well, clean it up. So you do something, get rid of square roots. That's not too bad. Square both sides. Expand, rearrange the x squareds, y squareds, z squareds, all cancel out. And then after a moment or two, you get the answer. Now, this is not so bad. This definitely works, and it gets you what you need. But we're not going to do it this way, because I want to say, look, I want to use the geometry. And you'll get the same answer, but I think slightly more elegant. So, what's our thinking? Let's start with our points. And so we're in space. So here's our point P, 3, 5, 4. And here is our other point Q, minus 1, minus 6. And we say, okay, can we think of any point which is equidistant from P to Q? Any point at all? Well, I think we can think of one. Something that's sort of halfway in between. So we can apply the midpoint. So if we do the midpoint of P and Q, what will we get? Well, essentially the midpoint formula says you average the coordinates, yes? So you take 3 plus -1 divide by 2, comma, 5 plus -1 divide by 2, and that's the y-coordinate, and then 4 plus -6 divide by 2, and that would give you what? Well, okay, 2 over 2 is 1, 4 over 2 is 2, 4 minus 6 is minus 2 over 2 is minus 1. So here, this is a point on the plane. Because it's a point which is equidistant, we're finding a plane, that's one of our points. Now, that's good news. Now the question is, how do you find the other points? Well, let's think about what's true about our plane in this situation. So if we were to now sort of do a sketch and say, okay, what's true about the plane that we are going to end up with in regards to what we currently have? And hopefully you're going to get some pictures suggestive. If not, this becomes a harder problem. But think geometrically, right? If it helps, think if you have 2 points on the z-axis. So you have a point up here and a point down here right below it. There we go. What's the plane of the points for equidistant? So that if you go them out, you'd go the same distance to travel there. What do you get? Something right in the middle. And what's the geometry saying? It says it's perpendicular. So this line segment between P and Q is perpendicular to the plane. And at that point, you're like, oh, well, that's cute. That's cute. But then you're like, oh, no, that's more than cute. What do we need to make a plane? We need a point and a vector. Now, when we talk about vector, we're saying a perpendicular vector. So, idea. Let's take a vector that goes between our 2 points. We can even go from the midpoint if we wanted to. So, what's our change? From P to Q, well, we go from -1 to 3. That's a change of 4. -1 to 5. That's a change of 6. I don't know why I'm getting so nervous. -6 to 4. That's a change of 10. 4, 6, 10. Now, this is a normal. And we don't have to use this one. We can use any multiple of it. So we can use, if we scale, we can use here, we can pull out a factor of 2. So 2, 3, 5. So now we have the normal and the point. We have everything we need to make this plane. And okay, so what do we have? Well, this gives us our coefficients for x, y, z. So 2x plus 3y plus 5z equals something. Now, what's the something? Okay, so we'll put it in. 2 times 1 plus 3 times 2 plus 5 times -1. And if we do this, we get 2 plus 6 is 8 minus 5 is 3. Okay, so the something is 3. And, thank goodness. So that's good news because we wanted to have a 3 there. So we actually are done. Now, what would have happened, let's just do hypotheticals, if we said, well, let's use this 4, 6, 10. So let's do that. What would have happened? Well, we would have had 4x plus 6y plus 10z equals something, right? We just need a normal. Now, plug in the point. And we'll get 4 times 1 plus 6 times 2 plus 10 times negative 1. That's 4. And plus 12, that's 16. Minus 10 makes 6. You say, okay, that's our plane. Then we check, does it match? And you'll notice here, they actually went out of their way to specify this number has to be a 3. Now, the reason they did that is that they wanted a unique answer. Because you could scale, right? This formula right here is the same as that formula right there. And so they said, well, we want to make it super easy, unambiguous. We look at it and we know. Because I'll let you in on a little secret. We don't read every single thing you write down. We look for key markers. And one of the key markers is, did you get the right answer? And then we just say, okay, did you get some of the right steps? And so we want to just say, okay, we have the right answer. So now you might say, okay, well, great. Well, what if I had done that? Would I box this answer? And the answer is no, because it doesn't have the right form. So we don't give up. We say, well, okay, I got 6. I need 3. What do I do? I don't subtract 3 because I don't want any constant on this other side. So I get there by scaling. So if you times it by half, then you get, 4 times a half is 2, 6 times a half is 3, 10 times a half is 5, 6 times a half is 3. So scale, and you'll get what you need. All right, and there you go. So that's how you do it geometrically. If you ran through this, you would have gotten the same answer. And it doesn't say you have to do it geometrically. So do what you're comfortable with. As long as you follow the instructions and answer the question, you get the points. All right. Let's keep moving forward. Give the Cartesian form of the equation rho equals 4 cosine phi sine squared phi times 8 minus 3 sine squared theta, and classify the quadric surface it defines. Now, there's some clues here. We see certain I'm trying to say symbols, and it's coming out as thimbles, and I apologize. So we see rho, we see phi, we see theta, right? When we see those symbols, we're like, oh, what's happening here is that we're starting in spherical, and so we say, okay, so we are currently in spherical, and now we need to get to Cartesian. Okay, so we need to know, how do we make an adjustment? So there's some basic formulas for spherical. One of my favorites, rho squared is x squared plus y squared plus z squared. We also say rho cosine phi, that's equal to z or z. Rho sine phi, that's equal to r. And now what happens is once you have r, because you also have these facts from your polar, x equals r cosine theta, y equals r sine theta. And if you're nervous, everything I'm writing down here is it's on the formula sheet, so we don't have to be nervous. So what do we get? Well, we get that x equals rho sine phi cosine theta, and y equals rho sine phi sine theta. Okay, so that's sort of something we're going to keep in the back of our mind. Okay, so we have these formulas for helping us to translate. Now, I'm not a big fan of fractions, so I'm going to get rid of the fractions. And in this case, I think the easiest thing to do is what I would call cross multiply. So since we have two things equal, we cross multiply, no more fractions, life is good. All right, so here we go. We're going to get that rho sine squared phi times 8 minus 3 sine squared theta. All right, so just multiply is equal to, and on this side, 4 cosine phi. Okay, well, that's a little bit better because there's no fractions, but it would be nicer if we had some things that looked like these expressions. And I see a cosine phi, and really the only place cosine phi shows up is it's attached to a row. So I'd like a row there. So what should we do? Let's put a row there. I like your thinking. How do we do it? Well, let's multiply everything by row. Okay, so we're going to multiply both sides by row. So we now have rho squared sine squared phi, 8 minus 3 sine squared of theta is equal to 4 rho cosine phi. And this will put us in our happy place. We see rho cosine phi. That's good. On this side, well, let's do a little bit of distributing here. So we have 8 rho squared sine squared phi minus 3 rho squared sine squared phi sine squared theta equals 4 rho cosine phi. And I think we can make progress now. Using what we've written down, let's see how far we can get. Now, we've already been talking about the rho cosine phi, so let's go ahead and just jump on that one. Rho cosine phi, that's going to become a z. Good, 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 good. Now, let's jump over to here. We have rho squared sine squared phi. That can be thought of as rho sine of phi quantity squared, because we just think of the squares, and we say rho sine phi is the r. And we're like, oh, so this is like r squared. And then we're like, oh, that's not very Cartesian-y, but it's very polar. And r squared becomes x squared plus y squared. Nice. Okay, so we have an x squared plus y squared there. Okay, now on the other hand, what do we have here? Well, rho squared, sine squared, sine squared. So everything's squared, so we can think of this as rho sine phi sine theta squared. We say rho sine phi sine theta, that's showing up over here. All right, so this is y squared. Okay, so what do we have? We currently have the following. We have 8 times x squared plus y squared minus 3 times y squared is equal to 4z. Now, let's do one more thing before we box this. We have the 8 we can distribute through. So we have 8x squared plus 8y squared minus 3y squared equals 4z. And we can put those together. So you get 8x squared plus 5y squared equals 4z. And we can put the z, make the coefficient 1. So we get z equals, dividing by 4, 8 divided by 4 is 2x squared plus 5/4 y squared. So that is a lovely form that we can use to write the formula for our tangent line. Okay, good, good. Now, that does this piece, the Cartesian form of the equation. But there's another part. Yes, you saw it, right? There's a word and, right? So we have to do a second thing, classify the quadric surface. Now, there's a clue, something that we can catch on really quick. Do you see how there's z? Not z squared, just z. So usually when we see that, that says, oh, hold on, you're thinking of some kind of paraboloid. And we look and say, well, yeah, we see a z and an x squared and a y squared. So it's like, oh, this is definitely paraboloid. But now, which kind? Is it like a bowl, or is it a saddle where in one direction we go like this, but the other direction we go like that? And so to do that, we look at how do the signs of the things compare. It's plus plus. So what kind of shape do we have? That would be an elliptic paraboloid. So that's the shape. And put another way, if you choose a value for z, like z equals 1, 2, 3, something like that, what you see is your slices look like ellipses. So that's why we call it an elliptic paraboloid. If your slices look like hyperbolas, we'd call it a hyperbolic paraboloid. But anyways, there you go. So I think mostly the key is, clean it up, start by getting rid of fractions, and oftentimes you might say, do I need another row? And if you do, add it, and then just start to say, well, okay, how can I put my pieces together and get what I need? All right, well, great. Fun problems. Let's keep going. Consider the quadric surface x squared over 4 plus y squared over 16 minus z squared over 9 equals 1. Identify which conic section is determined by the intersection of the quadric surface with the plane x equals 4, y equals 8, and z equals 6. So we have some shape, some strange, totally unknowable shape. Now, if you've been doing this for a while, you might say, oh, it's not actually totally unknowable. It turns out that this is going to be some variant of what's called a hyperboloid of one sheet, but opening up in the z-axis. But maybe we don't know that. So let's pretend like we didn't know this is the shape. And what are we after? We're saying, well, what are the conic sections that we're going to see? Okay, so before we figure things out, let's just remind ourselves what the conic sections look like. So there's a couple of cases. If you see something that looks like ax squared plus by squared equals 1, and here I'm going to assume a and b are positive numbers. This is what you would call an ellipse, all right? So that's that form of the conic section. And if you say ax squared minus by squared equals 1, or you see minus ax squared plus by squared equals 1, these are what we call a hyperbola. All right, so we have ellipse and we have hyperbola. And now if you see y equals ax squared or x equals ay squared, these are what you call a parabola. So these are the basic ones that you might interact with. Now, that definitely doesn't capture everything that could happen, but that's what we're looking for. So if both of them are squared, we basically say, okay, is it a plus plus or is it a plus minus? Right? Plus plus, ellipse, plus minus, hyperbola. And if we get some non-squares, we're probably going to head to parabolas. It's unlikely because everything here involves squares. So let's go through our cases. All right, so part A, we're doing x equals 4. So how do we do this? Well, the answer is plug in 4. All right, so we plug in 4. And what does that give us? Well, it gives us 4 squared over 4 plus y squared over 16 minus z squared over 9 is equal to 1. Now 4 squared over 4 is 4. Now you can rearrange, you can move the numbers and variables around, and if you do that, you get the following. This will be 4 subtract 1 makes 3 is equal to, and here minus y squared over 16 and plus z squared over 9. So I'm putting it here. I can divide by 3, but I only need to go as far as to know what do I see. And the key here is that there can be solutions. There are sometimes when it just won't have any solutions. It's empty. And that can happen, for example, if you have a hyperboloid of 2 sheets. And you say, oh, I sliced and I went through the middle. But there can be solutions. And I see I have different signs. They're both squares, so it's hyperbola. All right, so we say that for A, we are a hyperbola. All right, so that's for part A. Now, for part B, what do we have? Well, we're going to hit the plane y equals 8. Okay, so we do the same thing, y equals 8. So we have x squared over 4 plus 8 squared over 16 minus z squared over 9 equals 1. Well, we're just, again, 8 squared over 16. That actually turns out to be 4. All right, 64 over 16 is 4. We'll do the same, right? We'll just move this around, move that around, move that around. And what will we get? 4 subtract 1 is 3. And here, what will we see? Well, when we move the terms across, we'll get a minus x squared over 4 and a plus a z squared over 9. We say, okay, again, we get solutions. Minus plus, that's hyperbola. All right, so cool, hyperbola. And one more to go. Okay, so the last one, C. All right. That's our plane Z, or Z, equals 6. So we plug it in. So we get x squared over 4 plus y squared over 16, and then minus 6 squared over 9 equals 1. Now we'll move the constant across. And so what does that become? X squared over 4 plus y squared over 16. 6 squared is 36 divided by 9 is 4. Add equals 5. Well, what do you have? Plus plus squares. This has solutions, right? It's not like a negative something and a negative something equals a positive. That has no solution. This has solutions. So we say, this is an ellipse. Or like, perfect. That's what we think. And it matches with the picture, right? Because it's saying slice up here, and what will you see? You'll see an ellipse. And so, good. Now, you might say, okay, does all of this definitively tell us it's a hyperbola of one sheet? Well, not necessarily, because we may have sliced high enough up that we have a hyperboloid of 2 sheets. It's just that we skipped the zone where there's nothing in the middle. But it certainly is very suggestive. And so, yeah, if you can identify before you start, that definitely gives you a leg up. But even if you can't, really what's going on, when you're plugging it in and saying, what does it look like in a plane? Just say, okay, plug in that value. And now you reduced it to a smaller dimensional problem. So just make sure you're familiar with ellipse versus hyperbola versus parabola, and you can identify what kind of surface you're dealing with. All right, good. Well, let's keep moving along. Find two of them, integer values of t, so that the tangent line to the curve, and it's this curve, 3 plus 2t, 3t squared plus 7t, and 8 minus 3t, contains the point 9, 0, negative 1. All right. So, what are we looking for? We need to find values for t so that the tangent line contains the point. Okay, come on, Steve, come on. But what does that mean? So, what we'll do is we'll say, instead of just sort of like randomly guessing values of t, there's probably not going to be terrible numbers. Let's be systematic about it. So in other words, let's make the group of all tangent lines. Okay, so what do all tangent lines look like? So a generic tangent line has the following form. It looks like we have some point, and I'm going to use the symbol a, so a specific value of t. So we have at time t equals a, looks like r of a plus, and I'm going to use a different symbol than t. Let's use s r prime of a. So this is saying that, hey, there's a time associated with your curve. There's a time associated with your tangent line. And so s is the time I'm going to associate with my tangent line. So for us, we can even go a step further and say, well, we know what r of t is. It's right there. I mean, if they didn't tell the line, tell us this parametric curve, we couldn't do anything. 3 plus 2t, comma, 3t squared plus 7t, comma, 8 minus 3t. And r prime of t looks like, well, it's the derivative. Derivative of 3 plus 2t, 2. Derivative of 3t squared plus 7t, 6t plus 7. Derivative of 8 minus 3t, minus 3. Okay, so plug that in. So we update. We have 3 plus 2a, comma, 3a squared plus 7a, comma, 8 minus 3a, plus some multiple s, that's our other time, 2, comma, 6a plus 7, comma, negative 3. Now, those are our tangent lines. And as s varies, we get all the points. So now we found a generic tangent line, which really means, hey, I've got all of them. Which ones do we want to keep? Well, we want to make sure we contain a specific point. So we say, hey, I know, if I contain the point, then that must mean that there is some combination so that I get 9, 0, negative 1. So this right here is saying that 9, 0, negative 1 is a point on the line. Okay, so what do we need? Well, so the real question is the following. For which values of a is this possible? All right. For which a? Now, we don't really care the values for s, so for which values of a does this work? Or we can say, does this happen? Now, how do we figure that out? Well, we're going to write down a series of equations. And we do it by looking entry by entry. So let's look at the entries for x. We have 3 plus 2a plus 2s has to equal 9. Okay, that's the x entries. Don't forget the s will distribute through. Then the y entries, 3a squared plus 7a plus s times 6a plus 7 has to equal 0. And the last one, 8 minus 3a minus 3s, it has to equal minus 1. Okay. Good. Now, well, let's see what there is to see. If we start playing with this, let's look at the first and third equations, because those seem to be the easiest to move stuff around. We move the 3 across, then that becomes 2a plus 2s equals 9 minus 3, which is 6, or a plus s equals 3. Now, come to this one. Move the 8 across, minus 3a minus 3s would equal negative 9. Divide by negative 3, we get a plus s equals 3. So we're like, cool. All right, well, that tells us something. It tells us a plus s has to equal 3. Now, what are we after? We're after which values of a does this happen. We have one more equation, So what we can do is we can say, let's get this down to a single variable. And which variable do we want it to be in terms of? We want it to be in terms of a. So let's replace let's replace s in terms of a. So if a plus s is 3, then that tells us that we can write s is 3 minus a. That will definitely satisfy the first and the third equation. Now we just need that last equation to hold. So what do we have? Well, we have the following. We have 3a squared plus 7a plus s, which is 3 minus a, times 6a plus 7 equals 0. All right. Well, let's cross our fingers and hope nice things happen. Well, you know, if you live a good life, nice things should happen. 3 times 6a, 18a. 3 times 7, 21. Minus a times 6a, minus 6a squared, minus a times 7, minus 7a. And we still have the 3a squared and the plus 7a. And okay, so we expand and we see, aha, the 7a's cancel. That's good news. 3a squared minus 6a squared. That's minus 3a squared. We have a plus 18a, and we have a plus 21. And of course, we still have the equals 0. Okay, this is feeling pretty good. For one thing, it looks like something we can solve. It's a quadratic. And moreover, quadratics have 2 solutions. And we're like, yeah, okay, we're on track. Well, I like to put a 1 in front of my a squared. I currently don't have that. I'd like it to be there. Can we make it that? Yes. So we would multiply by negative a third. So if we did that, everything gets multiplied here by minus 1/3. So we get a squared minus 6a minus 7. All right, and now this is the real moment of truth. We know there are 2 solutions. We know they have to be nice because we were told they were integer. So it's got to factor in a nice way. So a and a. So we need 2 numbers that would multiply together to give negative 7, but would add together to give negative 6. I'm thinking negative 7 and plus 1 could do it. So let's check. A squared, good. Plus a minus 7a is minus 6a, and minus 7 times 1 is minus 7. That's all good. So now we say, okay, aha, what does that tell us? Well, it tells us that a minus 7 equals 0, or a plus 1 equals 0, right? Because product of something equals 0. One of the terms equals 0. So we get that a equals 7, or a equals negative 1. And those will be our 2 times where it all works. Probably not the values you would have guessed. You know, if you said, well, let me just start testing, it would have taken you some time to get to these numbers. Because I wouldn't start by saying, let me guess something near 7. I would just start, well, let's try 1, 2, 3. You know, it took time. But there's a way to do it systematically. So if we're after a tangent line that has a property, how do we do it? Find all the tangent lines and then say, okay, given that it has this property, what are the constraints that forces? And then reduce. So that's the idea. It's a good idea, and it works. And, well, those are the ones we like the best. Ideas that work, they're our favorite kind. All right, well, let's keep going. Find the distance d between the parallel lines. So we have x equals 3 plus 2t, y equals 5 minus 3t, z is 4 plus 6t. That's our first line. X equals 7 plus 2t, y equals 2 minus 3t, and z equals 7 plus 6t. That's our second line. Now, why do we know that they're parallel? Because they tell us that. And what it really says is look at the direction vector. So you have the 2, -3, and +6. That's your direction vector of your first line. And you compare it to the 2, -3, and +6. That's the direction vector of your second line. Okay, so that means they have the same direction vectors, which is even stronger than what we really need. We just need to make sure that their direction vectors are parallel to each other. All right, so, well, what's going on? We're in our three-dimensional space, and we have two lines. Say, okay, here's line 1, and running parallel to it is line 2. Now, we're after our distance d. So in other words, d is this distance between the two lines, which, forms a right angle. How do we do it? Well, there's a couple of ways, as there almost always are, but one of the ways we can do it is use our formula sheet. So if we're after distance, which it tells us we are, there's a nice nifty formula, and it has a little shorthand. So this dot and a line here, it's like, oh, hey, that's a point and a line. And it looks like the following, and I don't know if I'll have it exactly the way it's written in the formula sheet, but it'll be close enough. It's U cross PQ divided by magnitude of U. Okay, so there's a couple of things that you're probably thinking of. Wait, that's point to line. We need line to line. And spoiler alert, we can reduce our problem to point to line, right? Because I can come here and say, look, that distance will just carry it. It slides all the way down. I can just move this up and down. So regardless of which point I pick on one line, it's always the same distance to the other line. So, idea, I'll just say, if this is, say, L1 and this is L2, I'll pick a point on L2. And so all I have to know is what's the distance from this point to that line. Okay, well, is there an easy way to get a point on L2? And the answer is yes. Yes, there is. Because it's stored inside the formula for the line. So we happen to know that there is this point 727. That is a point on L2. And in terms of this formula here, this is Q. Now, what are the other pieces? What's P? Well, P is a point on line 1. Okay, well, how do we get a point on line 1? It's again stored here. It's 3, 5, 4. So we have 3, 5, 4. Okay, cool. Now, what's U? Well, that sounds like a philosophical... Oh, no. What's the vector U? Oh, yes, the vector U. Sorry. That's not the U yourself, U. Okay. The vector U is the direction vector of the line. So P is point on the line. We'll make some notes here. Q, point off line. And U is the direction vector of the line. Those are the pieces that we have here. So U, we've actually marked. So U, it's, maybe it's this vector here, and it is 2, -3, 6. Okay, so we're going to follow through what this tells us to do. Says, find this vector, P to Q. And we say, okay, what is that vector? So the vector PQ looks like, well, 7 subtract 3, right? We're looking at change. Went up 4. 2 subtract 5, down by 3. 7 subtract 4 is 3, right? So you can take n minus beginning, or you can just say, I start here, I got there. What I need to do, I need to add 4, needed to subtract 3, needed to add 3. Okay, so there's our PQ, and we've already marked our U, but we didn't label it as such. So we'll label it now u, our direction vector, 2, minus 3, 6. And we're ready to just chug away. Into the machine it goes. And we're going to have a grand old time. All right. So, and let's see what we are going to have. We're going to do a cross product. And this is one of those things that hopefully after last week we're pros at. Okay, so we're setting up our 3 by 3 matrix. 2, minus 3, 6, 4, minus 3, 3. Shoop. Okay. And I like to do it by diagonals. There's other ways to do it. Some people do this by cofactor expansion. The thing is, as long as you get the right answer, we're happy. You know, that's the thing. We want you to get the right answers. And, okay, so I times minus 3 times 3, that's going to be negative 9i. And then we have j times 6 times wraparound 4, and that's going to be 24j. And k times 2 times negative 3. So that's going to be minus 6k. Right? Those are the ones that we get from going what I like to call downhill. And now we'll go in the other direction, uphill. And same idea, 4 times minus 3 times k. Well, okay, that's minus 12k, but subtract it. So subtract negative 12k. Right? We add the downhill, we subtract the uphill. And okay, then what? Well, we have minus 3 times 6 times I. That's negative 18i, so we're subtracting negative 18i, which will make it a plus 18i. And then the last one, 3 times 2 times j. That's a 6j, but we got to subtract 6j. All right, so when we put all of this together, what do we have? Well, we have minus 9. Minus minus makes plus 18, which would give us a grand total of 9. 24 minus 6, that's 18. Yes, 18, yeah. And then minus 6 plus 12. Well, that would be, 12 minus 6. That's 6. Okay, there we go. 9, 18, 6, which, by the way, these all have factors of 3. So that's 3 times 3, 6, 2. All right, now, what can we do? Well, we should check ourselves. So, quickly, take the dot product. I don't need to worry about the scaling factor of 3. We're going to get 2 times 3, 6, minus 18, 12. 6 minus 18 plus 12 is 0. Nice. 12 minus 18 plus 6, 0. Nice. All right. That should just become a habit. You know, check your work. Look for little things that say, okay, what is a way for me to make sure I did this step right? And just get into the habit. The sooner you catch mistakes, the better. Now, that is almost our answer. So our distance, d, is the magnitude of this vector, 3, 3, 6, 2. All right, that's the one coming from the cross product. Divide by the magnitude of this vector, 2, negative 3, 6. Now, here's the great thing about magnitude and scaling factors. This term here, this 3, can come out. So scaling factor can come out. Now, it has to come out as a positive. So if it was a negative 3, it'd have to come out as positive 3. But still, it can come out. So we get 3 times the magnitude of 3, 6, 2, divide by the magnitude of 2, negative 3, 6. The reason I like to do that is it makes the numbers I'm going to have to work with smaller, also known as less likely to make mistakes. And I'm a big fan of the less likely to make mistakes doctrine. Okay, so we have 3 square root of 3 squared is 9, 6 squared, 36, 2 squared is 4, downstairs, square root, 2 squared is 4, negative 3 squared is 9, and then 6 squared is 36. And now you say, aha, 36 plus 4 is 40, plus 9 makes 49, and that means you get a square root of 7. But you also have a 36 plus 4 plus 9, that's also a 7. So it's really 3 times 7 over 7. Those cancel, and we're left with 3. Wow! Wow! What a nice number! A great number. And on a side note, that is not the distance between P and Q. P and Q are further apart. You can actually do that. You can say, well, it would be the square root of 16 plus 9 plus 9, which is definitely bigger than 3, right? Even as soon as you said square root of 16, it's like, yep, you're bigger than 3. And so you can't just say, oh, hey, I just picked 2 points on those 2 lines and just take their distances. No. That's not going to find you the minimum distance unless you rigged the problem and got really lucky, which is not going to happen. But this process will find it. Now, there are other approaches. I am not saying this is the only approach, but this is the one where we have a nice formula, and it's handy. It's right there. So let's use our tools. Use our tools, and let's get comfortable with our tools, and so that we can succeed. I like success, and I want you to succeed as well. All right, let's move along. 2 planes intersect at a right angle. Well, that's good. I'd be worried if they had intersected at a wrong angle. Oh, wait, no. That means they're perpendicular. Okay, we'll get to what that means. And their line of intersection has the equations x equals 3 minus t, y equals 1 plus 2t, and z equals 4 plus t. Okay, so, all right. And so they gave us the parametric form for the line of intersection. That's good. If one of the planes passes through the origin, find the equations of both the planes. And we have to write our answers in the form ax plus by plus cz equals d. Now, there's a lot going on here. And so I think this one is not such a bad problem to actually do. We're not going to be here for hours, but we have to make sure we parse it and think about how we can approach solving it. So let's think about where we can begin. We know we're looking for 2 planes, but we don't have to find them both right away. We're told they intersect at a right angle. So what does that tell us? Well, it tells us that the normals, and when I say normals, I mean the normal vectors of our 2 planes, they're perpendicular. And we're like, oh, well, that's a good thing to remember, because we like when things are perpendicular. The reason we like things being perpendicular is oftentimes we can use cross product to find them. Okay, we also know that there's a line that the planes have. So we have, okay, they both have the line. We have x equals 3 minus t, y equals 1 plus 2t, and z equals 4 plus t. Now, in particular, when it comes to that says they both have the point. So we know a common point to both planes is going to be a point, not a vector, 3, 1, 4. I'm just so excited to write vectors. And there's a vector that we know is in both planes, and that's the direction vector. All right, so that's minus 1, 2, 1. So in particular, now I wrote it as a point. Come on, Steve. You can do better. Point, vector. And here, this is also perpendicular to both normals. Right? So, good. There we go. That's information that we've been given. Now, we have one other thing. one of the planes passes through the origin. And we're like, oh, okay. One of the planes passes through the origin. Okay, so let's focus on that. So the plane through the origin, what do we know about it? Well, we know it has the point 0, 0, 0, but it has this line, so it also has the also has the point 3, 1, 4, and there's a vector -1, 2, 1 that's in the plane. That's the direction vector of the line. Now, here's the thing. If I have 2 points, what do we have? We have a vector. So say, aha, 3, 1, 4. This is also in the plane. So the vector from these 2 points is in the plane. So I guess we'll make a note. Vector between these 2 points. That's a lot of writing, but that's okay. Is in the plane. And there we go. Okay, so what do we have now? We've got 2 vectors in the plane. And they're not the same vector. This is good news. This is good news. And you're like, Steve, you're kind of acting a little bit abnormal. Or am I acting normal? Exactly. Once you have 2 vectors in the plane, cross them and you'll get the normal vector. Okay, so our big aha, and it's a wonderful aha, is to say, okay, so the normal for this plane is, we're going to take these 2 and cross them. -1, 2, 1, cross 3, 1, 4. Okay, well, another cross product. Ah, what a lovely day. So I, J, K, -1, 2, 1, 3, 1, 4. All right, do your diagonals. I times 2 times 4, 8I. J times 1 times 3, 3J. K times -1 times 1, -K. Go uphill. 3 times 2 times K, 6K, but you need to subtract it. Right? You add your downs, subtract your ups. 1 times 1 times I, that's I, subtract it. 4 times -1 times J is -4J, but subtract it. And so what does that give us? Well, 8 minus 1 is 7. 3 plus 4 is 7. Minus 6. -1 minus 6 is -7. And, or I can pull out a 7. 1, 1, -1. Okay, so my claim is that this is the normal. Now, any scalar can work, so we're going to take advantage of that and say, hey, just do the easy part. Make it look like a nice numbers. So 1, 1, -1. Okay, now let's check. Is this perpendicular? -1 plus 2 -1, 0. Good. 3 plus 1 -4, 0. Good. So there's our normal. We can use 1, 1, -1. We don't need the 7 because we can scale. Remember, normal vectors aren't unique. We can scale. So once we have our normal vector, we can write down our equations. We get the equation x plus y minus z equals something. Now, what goes in the box? What goes here? Well, pick a point. Is there a convenient point? Well, we have 2 points, and 0, 0, 0, ultra convenient. 0 plus 0 minus 0 is going to give us 0. So, the plane through the origin that we were looking for looks like x plus y minus z equals 0. All right, so that is one of our 2 planes. But we're not done, because there was a second plane. Okay, so then we have to find the equation of both planes. Now, what do we know about both the second plane? Well, notice the second plane, it has to have its normal is perpendicular for the first plane, right? So for the second plane, we know that the normal is perpendicular to the normal for the first plane, so it's perpendicular to 1, 1, minus 1. And it's also perpendicular to the direction vector, minus 1, 2, 1 of the line, because the line is in the plane. So, I say, aha! Whoa! I have now found two things that are perpendicular to my normal. This is a good thing. This is a great thing. Because what can we do at this point? Cross product. Okay, so here we go. We're going to take the cross product of 1, 1, minus 1, cross minus 1, 2, 1. And gosh, we're going to get good at cross products on this problem. 1, 1, minus 1, minus 1, 2, 1. And okay, so what does that turn out to be? I'm just going to go through here. I. Then I'm going to get plus j plus 2k. Then we're going to subtract negative k. Going to subtract a negative 2i. And then we're going to subtract j. So we're getting a 3, 0, 3, or if you like, that's 3. Let's make sure we can see that. 3, 1, 0, 1. Well, let's quickly check. 1 plus 0 minus 1, 0. Minus 1 plus 0 plus 1 is 0. Good. So now we have our other normal vector, right? The normal vector for the second plane, so we can write down our equation. And we say, okay, so the equation for the other plane looks like x plus, all right, 0y for right now, plus z, right? The coefficients 1, 0, 1 equals something. Okay, and now the question, what's in the box? What's in the box? And how do we figure that out? Well, we have a point. We can't use the origin, but we can use that 3, 1, 4. And so this point here comes down. And what do we get? We get 3 plus 0 plus 4, which gives us 7. So what's our second plane? It's x plus z equals 7. And there we go. So our two planes, x plus y minus z equals 0, x plus z equals 7. They both are containing this line. They both have the point 3, 1, 4. They both contain the vector minus 2, 1. They intersect at right angles. Everything is satisfied. And there we go. Okay, so there was no one big step that was our great, like, aha. It's just one huge thing. It's lots of little things tied together. And it's just a matter of thinking, like, okay, what can I do? What can I do? In some sense, I think the big aha moment was to realize, hey, that plane where I know it goes through the origin, that's a little bit extra information because I have a point and a line. Point plus line, you can make a plane. So that's why we did the plane through the origin first and said, hey, wait a second, now that I have that plane, that helps give me information on the other one. So there's a little bit of think about the order you do things. We could not have found this plane before we found that plane. So it's good to think about things. And we hope you think about a lot of things. That's one of the reasons why you're here. So keep doing it. We like it. All right, let's move along. A plane with the equation ax plus y plus cz equals 4 is tangent to the curve r of t is t plus 2, 2t squared minus t, t cubed minus t plus 3 at t equals 1. find A and C. All right. And cool. Okay, so we're looking for A and C. Now, in particular, it's these coefficients here. There's a little bit going on here. I just want to point out. Now, normally when we talk about a curve, there's not a unique plane tangent to a curve at a point. So what they've done here is they've actually said, well, I've actually given you, it's not any arbitrary plane. I'm going to give you a little bit more information. So because it's a restricted type of plane, that's how you have a hope. Don't think that, generally speaking, that there's a unique plane that's tangent at any particular point. That's not quite true. So I just want to be a little bit careful here. What do we have? Well, if it's tangent, it must contain the point and it must contain the direction vector. So we're going to compute those two things. So we have our r of t. I'm going to write that down again. So r of t is t plus 2, 2t squared minus t, t cubed minus t plus 3. And r prime of t is the derivative of t plus 2 is 1. Derivative of 2t squared minus t, 4t minus 1. Derivative of t cubed minus t plus 3, 3t squared minus 1. And we're going to plug in our value, our time equals 1. So what's going on here? At time 1, r of 1 is 1 plus 2 makes 3, 2 minus 1 makes 1, 1 minus 1 plus 3 makes 3. And here, this is a point on the plane. Now, r prime of t is 1. 4 minus 1 makes 3. And 3 minus 1 makes 2. What is this? It's a vector. So this is a direction. Now, what is it? It's a direction in the plane. And we say, okay, well, what must be true with these things? Okay, well, we can say we know that this point, 313, has to satisfy this equation. So we are going to say, plug in 313, and we're going to get 3a, right, because x is 3, plus 1, plus 3z, 3c, 3, 1, 3. So 3a plus 1 plus 3c equals 4. Or you can subtract 3a plus 3c equals 3. Or a plus c equals 1. Okay, so that's a condition. So a and c can't be arbitrary. We need to have that a plus c equals 1. Still not enough, but we haven't used this information. We know that 132 has to be a direction in the plane. So how do we know that? Well, that tells us here that 132, the direction, has to be perpendicular to the normal. And what's the normal? Well, we read it off. It's A, 1, C. Okay, so great. And that's because we're in the plane. So we get that 132 dot A1C, which is A plus 3 plus 2C has to equal 0. Or A plus 2C has to equal negative 3. Okay, and that's the second equation. And now we're in our happy place. 2 equations, 2 unknowns. We like that. All right, so we just have to solve that. All right, so A plus 2C equals negative 3. A plus C equals 1. I try to shoot for elimination, and I see, they both have A's. Let me subtract the second equation from the first equation. The A's go away. 2c subtract c gives us just a c. Minus 3 subtract 1 is minus 4. Okay, so c is negative 4, but we now plug that into the first or the second, doesn't matter which one. Maybe the second's a little bit easier. A plus a negative 4 equals 1. Add 4, we get a equals 5. And so we say, okay, so there's our c and our a. Let's just put them together and make a nice little box. So a equals 5 and c equals negative 4. And there we go. All right, so this is not so bad. It's just a matter of saying, okay, we have a tangent. That means we have two pieces of information, point and direction. How do we put that into our plane to get our two unknowns, A and C? And then once we understand how to put it all together, it comes together in really quite a beautiful way. Life is good. Life is wonderful. All right, let's move on to the next problem. Find the point on the plane 2x plus 3y minus z equals negative 5 closest to the point 170. Now, so closest, in some sense, was like, oh, we're trying to minimize the distance. Like, yes, we are. So you might say, oh, should we use our distance formula? No, we shouldn't. This is not a distance formula type question. So, okay, so we're not finding a distance. What are we finding? It's always important to understand what we're finding. We're not after a number, we're after a point. So our answer better be a point. So I say, oh, okay. So let's sort of reason, use some geometry here to think about our situation. So we have our plane, 2x plus 3y minus c equals negative 5. And we have a point. Okay, so let's put it up here. And of course, the picture is, I'm making it very simple and everything looks nice, but start with easy pictures. Now, we want the point in this plane closest to that point. Now, when you hear closest or nearest, you should say, oh, if I were to connect down to the closest point, what should be true? So this right here, this is our goal. We want to find that point. What's true is that this is somehow perpendicular. There's this nice notion that perpendicularness is associated with nearness. And we say, okay, well, that's interesting, because what can you do? Well, one thing you can do is we can sort of imagine that there's this line segment, but why stop? We should just never stop, never stopping, right? So it's like, oh, we could extend that. So, idea, can we find this line? All right. Well, what would we need? We need a point. Well, that's okay. We can do that because it has to have that point 170. Do we know a direction? Well, what's true about the line? It's perpendicular to the plane. What else is perpendicular to the plane? The normal. So the direction of the line has to match the normal vector. And again, direction vectors of lines and normal vectors, in both cases, they're not unique. So you might say, but wait, is it exactly the normal? Well, it's equivalent. They're parallel to each other. So it's 2, 3, negative 1. And now you're like, whoa, wait a second. Now we've got a point and a vector. We can definitely find this line. Maybe you're not convinced it's going to be a useful line, but at least I think I can convince you we can find it. And we say, all right, well, let's write down our equations. We have x, y, z. We put in our point, 170. And then we add to that our 2t, our 3t, and our minus t. And hopefully, this should look familiar. This first part, 170, that's our point. And then our second part, that 2, 3 minus 1, this is our vector. All right. And now we're like, cool, but how does that help us? Well, now we can think of our goal in a different way. Not as like, oh, let's find the nearest point in the plane to this other point. But now it's, where does this line intersect this plane? That's a little bit more palatable as a question, because there's not like, oh, nearest or closestness. It's just like, where do two things intersect? And to answer that question, we say, well, we know what x, y, and z look like as functions of t, and simultaneously we know a relationship between x, y, and z. So the intersection, we need to have both of these formulas holding. Or you can say both sets of relationships need to hold. So this is the great aha. So what we're going to do is we're going to plug in. So we're going to take 2 times x plus 3 times y minus z. And we're going to say that equals -5. Okay, so there's 2x plus 3y minus z equals -5. That's what a typical xyz on the plane satisfies. And here's an xyz on the line. So this must be true at the point of intersection. Now notice, one equation, one unknown. Just t. So we now do a little bit of cleaning up. We can distribute. So we say, okay, we get 2 times 1. All right, 2 times 2t. Okay, so we have 2 plus 4t, 3 times 7, 21. 3 times 3t is 9t. Minus t makes a plus t, equals -5. Okay, 4t and 9t and t all together make 14t, right? 4 plus 9 plus 1. 2 plus 21, that would be 23. Now we're going to subtract 23. -5, subtract 23 is -28. And so we get t, we can divide by 14, is -2. And you're like, yes, we've done it. That's the answer, right? No. What is that? It's a t. What are we looking for? A point. Oh, dang it. We were so close. But hold on. What do we know? Well, t just tells us, hey, you give me a t, I give you a point. So great. Now plug this into the line. And I say, okay, all right, let's plug this t into the line. And if we do that, we get our desired point. So what is our point? Well, so we're going to get x is equal to 1 minus 4, because that's 2 times -2. Y is equal to 7 minus 6, 3 times 2. And z is equal to minus 2 is 2. Or we get -3, 1, 2. And so our point on the plane that is nearest to the point 170 is the point -3, 1, and 2. Okay, that was it. That was, again, think geometrically. The closest, you're sort of like, there's an ist. It's like calculus, set up a function, take a derivative, like, But now it's like, hey, no, use geometry. Geometry is a wonderful tool, but you have to know how to use it and how to use it responsibly. All right, that brings us to the end of another fun set of problems. Thank you for joining me. Thanks for working hard, and I appreciate it. You're getting there. You're learning how to think, how to picture things, and work with things in 3D. It takes some time, but I know you can do it. You're wonderful. And I hope you're having a great time in the class, and I also hope that I get to see you again. All right.
Bye.